Okay, hello everyone, good morning. My name is Avi Ostfeld. I'm coming from the Technion Israel Institute of Technology. Thank you, Professor Juan. Thanks for inviting me. It's a pleasure being in Colombia. I'm enjoying every moment. So thank you very much for letting me have this talk this morning. Okay, the subject of my talk is management of water distribution systems, overview and challenges. As I said, my name is Avi Ostfeld. I'm coming from the Faculty of Civil and Environmental Engineering from the Technion, Israel Institute of Technology, that's the biggest technical university in Israel. It's located in Haifa, on the northern part of Israel, near the shore. And I'm a faculty member there, as I said. What you see here on the slide, that's obviously my email and also my webpage. I'm saying that because everything that is written here and everything that I will show here in this presentation, you can also find over there a lot of papers and stuff like this, which might be helpful to anyone who wants to see or to learn a little bit more. Okay, so here is the outline of my talk. I will start with introduction. I will look at 3 example applications and a few challenges on water distribution systems management, and an overview what I think is important and what still needs to be done. Now, I know that the audience here is a mixture. There are people here that are coming from industry, and there are people here that are coming from academia. I'm a professor. I have an academic hat, but I also worked in industry for 3 years. Perhaps some of you know, I was working with Tahal Consulting Engineers in Tel Aviv. I know they had some projects in South America as well. So what I'm trying to say is that I'm aware of the gap of what I'm going to show from the academic side and from the practical side. And I know that the gap is there. I mean, there is nothing to do. The gap is over there, and I'm aware of this. So the main message that I would like to deliver is more the conceptual things that I'm thinking of, and not so much on the technical things that are connected to what I'm doing. Because there are a lot of things which are technical that I will show. Some of them which are too technical, I will simply skip. All the references are on my website, so anyone who is interested is more than welcome to approach me or to go to see the papers and learn more. Okay, so we'll start with introduction. So again, this is more from a perspective, not too much from an academic perspective, but yet a little bit more than just a practical perspective. So if you're thinking on a water distribution system, you can think about it as a collection of nodes and links which are connected together. And this is not just water distribution systems. Any system which has nodes and links can be described as what we call a graph. You can think about a transportation system which looks like this, an electrical system, almost any system. Now, if we think on a behavior of a water distribution system, how does such a water distribution system is behaving? And again, this is also quite general. When we want to model a system, we need to look at the physical laws which describe flow and water quality distribution. This is and when you look on water distribution systems, if you look on electrical system, that you will need to know a little bit about the current, the voltage, and other things which are connected. If you are going to design something which is connected to transportation, then you will need to know a little bit about vehicles and loads of vehicles and stuff like this. The second thing that we need to know if we are looking on water distribution systems, we need to know something about the consumer's demands, which are driving the way that water distribution systems are behaving, and we need to know the system layout. Now, here is a simple example of a water distribution system, which is very simple, but it actually has all the components, as you know, that the water distribution system has, or the major ones. So we have here storage. We have here, say, 3 sources. This, for example, can be an aquifer that is taking water from groundwater. This can be a reservoir that is, or an aquifer that is taking water from here and here another one. And we can have here a tank, a storage tank that is filling during tariff hours which are very low and is supplying when tariff hours are high. And you can add here also reservoirs which are supplying water by gravity. I was yesterday at the utility that is supplying water to Bogota, and I'm aware of that most of the sources for Bogota are coming by gravity and coming by surface reservoirs. So we have pumping, we have different consumers, and we need to manage this system. Again, that's a toy example, a very small one, but yet quite general. Now, if you think a little bit about a water distribution system, and if you think about an electrical system, so what's the difference? Why do water distribution systems are more challenging to manage than other systems, at least from the perspective that I'm showing here? First of all, everything that is connected to flow and head. In water distribution systems, as you know, we have the Hazen-Williams equation, or we have the Darcy-Weisbach equation. Those are nonlinear equations. Those are much more difficult than if you are looking at an electrical system in which we have the Ohm law, which is sitting here, which is much more easy if you need to incorporate because that's a linear system. Now, this is one thing that we have, and in general, if you want to apply anything on a water distribution system or an electrical system, we need to follow the so-called Kirchhoff laws number 1 and 2, which I hope you remember. One is for mass continuity and one for energy continuity. So what is uniqueness or the differences between water distribution systems and electrical systems, for example? Why do water distribution systems are more complex? So here you can see there are 3 differences that I'm mentioning here. One is, as I said, the nonlinear head-flow relationship. So if you are looking at the energy in the system, it will go to Q, or the flow in the system, at the power of 2 or 1.852. We have storage in the system. We don't have storage in electrical system, at least not the way it's working in water distribution systems, and we have water quality issues. So usually, or these days, we are not just looking at problems which are connected just to flow and to energy or to head. We are also looking at problems which are connected to water quality, like free chlorine, turbidity, contamination that are coming into the system, anything that are connected to water distribution system, because what we would like to supply is a good service to the customer, which is not just the quantity and the pressure, but also the quality, the water quality. That's a prime objective. Now here's a little bit of a technical figure that you can see. What you see here, this is a very famous water distribution system, a test problem that was invented by, or first used by Alperovich and Shamir in 1977. And again, the details are not very important. What you see here, this is a constant head source, like a reservoir that is sitting high above the ground level. Here you have 6 consumers, and here the problem is to design the system at least cost. So you want to know what the pipe diameters should be here so that the cost of constructing the system will be minimum. And of course, you have here different demands here in the system, and the system is relatively easy because it has only one source and it is fed by gravity. You don't see here any pumping. But if you look here, this is the head at one of the nodes, node I, and this is the other head at node J. You can see here the nonlinear relationship between flow and between the difference in heads, and that's the resistance of the pipe, which is taking into consideration the pipe diameter, the friction coefficient, and the length of the pipe. Now, when you look at such a system and you want to design it, you want to find the optimal solution, then flow might reverse. So you might think that the flow should go from this node to this node, but when you end up, the flow might reverse. Because of that, you have here an absolute value, which from an optimization point of view, makes the problem very hard. And that is because if you are using any any methodology, any optimization methodology, you might get discontinuities because of this, this absolute value. Now, what you see here on this figure, this is, these are two decision variables that we are using here. And this is like the response function. So every point here is a possible solution. Now, I'm showing this figure, which is coming from this reference from Loganathan in 1995, Loganathan et al. What I would like to emphasize here is that the surface on which you are looking for the optimal solution is extremely not comfortable. It's not easy. It's like imagine that you are looking here for the lowest value on this surface, and you need an optimization model that will lead you to that direction. And this is because you have this absolute value here that is connected to the fact that flow might reverse. Now but this is only one part of the entire story. The other part is if you are looking at this system and you're also looking at water quality issues, it's not just that you have an absolute value, you can also have discontinuities. Because if flow is reversing, and this is a set of equations of a mass balance at a node, if flow is reversing, then the entire set of equations is changing. Now, we would like to do everything. We would like to do flow, we would like to do energy, we would like to know water quality. But this is what we are facing. This is a system that we need to work with. So just to emphasize that water distribution systems management from an optimization point of view, from a more theoretical point of view, is not an easy task. And because of that, at most utilities, what people are doing, and I was quite impressed yesterday when I went to Bogota and the water utility, and I saw the decisions are being made by results of a simulation model. That's very nice. That's very nice because a lot of times where I've seen people that are making decisions that are connected to water, they make decisions differently. But the fact that you are looking at a simulation model and you say, okay, I would like to do something, what do the simulation models tell me? And you have confidence in that simulation model, that's very nice. But that's obviously one stage further. Okay, now, the system that I've shown before, obviously that's just a toy system, a very small example, just to emphasize the points that I would like to show. But obviously every city looks like a spaghetti. Yes, a lot of pipes, a lot of reservoirs, and it depends to what resolution you would like to go into. So that's Baltimore and Maryland. This is Tel Aviv, where we did a study. This is about 100,000 nodes and 100,000 links. Now, of course, you don't necessarily need to look at each tap. You don't need necessarily to look at each pipe in the system. But those are the systems that we are looking at and we need to manage. Okay, now this is a very important figure. That's not a technical figure. That's a figure that is actually giving a map, the way that I'm looking at, on different problems which are connected to water distribution systems. So this is like an overview on what can be done in water distribution system and what already has been done. And when we'll come to the end of my talk and we'll talk about challenges, then I will go back to this figure and we'll talk a little bit about challenges, things that have not been done yet on water distribution systems or where gaps still exist. Now again, this is from an academic point of view. If you look on people who are doing this in practice, then a lot of things that have already been done in academic institutes still need to absorb in industry. And it takes time. And it takes time. One of the things that water utilities have, they're extremely conservative, and that's okay, because they are responsible on supplying water at adequate pressure and water quality. And once a decision is being made, that's not a game. I mean, you're supplying water, which is a very important commodity. That's obvious. Okay, now if you look at this map, I'm partitioning this map to three sections. One is problems which are connected to layout, connectivity, which node should be connected to which node. So if you have a water distribution system and you want to extend it, then the problem is connected to layout. Once you have the layout of the system, you need to decide on designing the system. What should be the size of the pipe? What should be the maximum power of the pump? And if you have a tank, what should be the volume of that tank? So you need to size the system. And after you do sizing, you're thinking about operation. How are you going to operate the system? Now, when you operate the system, obviously, and when you're designing the system, it's not just cost. You're not just looking at cost. Most of the times, cost is not the most important one. Most of the time, that's not the most important one, because it's not just a problem of cost. Most likely, the main problem or the main thing that you need to cope with is reliability. How do you supply water reliable? How do you construct a water distribution system and operate a water distribution system in a reliable way? So those are the three levels. In reality, there is only one level. Everything is connected together. But if you want to think about it as having layout, design, and operation, then it's easy to memorize it this way. Now, if you're looking at all these three problems, there are different problems that are adjacent to it. We'll come in a moment to this, deterministic and stochastic. You have problems which are connected to flow and head. You want to supply adequate water demands at minimum pressures. You have different types of water distribution systems. You can have systems which are branched. So if you have agriculture, you don't need to have any loops in the system. Branched systems are very cheap because you don't have these loops in the system. But if you're looking on an urban water distribution system, then you need to have loops in the system because you need to have the ability to supply water to consumers from more than one direction. So you might look at systems which are branched. They might be looped. They might be gravitational, just fed by gravity. And they might have pumping, and they might have storage in the system itself or not. It depends. For example, the water distribution system in Tel Aviv has no storage in the distribution system itself. Everything is supplied by gravity out of the system, and there is no storage within the system itself. So it depends. So you can cope with different types of water distribution systems that have this type of categories. Now, you can look at flow and head. You can add also water quality. As I said, nowadays we are looking flow, head, and water quality. The water quality that is supplied is a prime issue to consumers. You can look only on a one loading condition. Like, for example, most still design, when you're looking at a master plan, the pipes are being selected by looking just at the one or two loading conditions, an average loading conditions or an extreme loading condition, and you're assuming that if the system is working for an extreme loading conditions, then it will be able to work under any other condition. This might be true, but sometimes it's wrong. So it depends on how many loading conditions you are taking into consideration. And again, people are now more looking on the so-called EPS, extended period simulation, on looking on loadings which are changing over time. Okay, so number of loadings, you can take one or more. Now, you can look, what you see here, those are different problems which are connected to water distribution system. Maintenance, which pipe are you going to, which pipe are you going to replace and when? What are the priorities of maintenance? What type of maintenance are you going to do in the system? Yesterday, when I was in Bogota, I've seen that. That's a big problem. What priorities are you going to place to do maintenance? What pipes are you going to replace? What pipes are you going to strengthen, like doing a parallel pipe to an existing one? You have problems which are connected to aggregation. So if you look in the Tel Aviv water distribution system, you have 100,000 nodes and 100,000 links that we have modeled. But do you really need such a detailed model? Perhaps you need a model which is much more aggregated, which is much smaller. It depends what you want to do. If you want to do, for example, an optimal operation model, then perhaps that's not very important to look at each step. But if you look on a water security problem, which is connected to contamination water that is moving in the system, then this might be very important to do a very detailed model. So aggregation is another problem. We'll come in a moment to this one. Reliability, how do you supply water in a reliable sense? How do you define reliability? We'll come to this in a moment at one of the examples. And of course, reliability and cost are two competing objectives. Obviously, if you get a system with minimum cost, it will be the lowest in terms of reliability. If you are willing to have a higher reliability, you need to invest in extending capacity. If you want to extend capacity, it costs money. But then the system becomes more reliable. Another example are the storage in tanks. Tanks need to fluctuate between minimum and maximum. But if you look on system how they operate, tanks are not fluctuating. And they're not fluctuating because operators like to have the tanks full. Because if something has happened, they have a backup. So it's reliability and cost that are competing against each other. Coming back to unsteady. Unsteady is connected to transients. Water hammer in a water distribution system. If a pump, for any reason, stops working, and you have that wave going in the system, and everything is blowing out. So you need to defend the system again using surge control devices, and you need to cope with unsteady. Unsteady is very complex because it's not like simulating the system in steady state. You need to simulate the system for different waves that are moving in the system. So all the momentum that is in the system need to be absorbed once you have a failure of a pumping station or a valve that is suddenly closed, things like that. Security, water security. Water security in that sense is driven to some extent, or perhaps that's the most important driven factor are the 9/11 events. And people have started to worry on what's going to happen if a contamination might enter the system. It might be entering the system deliberately, but it might enter the system non-deliberately, just occasionally. And in Israel, for example, there are a few examples of contaminants that have been entering the system, not deliberately, occasionally, but still it happens. So for example, there was one example in which a fuel has to be filled a specific tank, and the operator selected the wrong connection. So instead of filling the fuel tank, he injected fuel into the distribution system. So people started to feel that they are drinking water with fuel. So that was really a proof of concept. Never mind. So this is connected to security. Now, all the things that I've said here are connected to deterministic. So if you assume that you know the demands in the system, the consumptions, but you don't really know the consumptions. You just know them in a specific range. Now, one other thing that I need to say here is that here, one thing that is missing here is leakage. Leakage doesn't appear here. That's also a problem. Or non-revenue water, that is also a problem here, and can be maintained by different activities, like actually managing pressures in the system and by doing valves closures or valve operation and stuff like this. But if you're going back to here the assumption is that everything is deterministic, but in reality, everything is stochastic. You don't know exactly what the demands are. You don't know exactly how consumers are going to react. So if you want to take those into considerations, things becomes much more complex if you want to manage a water distribution system. Now, the first thing that you must be able to do, no matter what system you are looking at, no matter if this is a transportation system, an electrical system, a building, whatever you do, the first thing that you must be able to do is to simulate the system. So if you look in different scenarios, like for example, you're replacing a pipe, or suddenly a pipe there is a burst in one of the pipes, so one of the pipes is being broken, you need to be able to simulate the system. And I know that reliability, for example, is incorporated in practice by looking at different scenarios. what's going to happen if that pipe is going to break, how the system is going to operate. So, and what you do, you're doing simulation. So you're doing simulation, so there is no way to talk on optimizing a system if you're not able to simulate the system. And optimization is not like something that, although I'm like advocating optimization, I'm not advocating optimization. What I'm trying to say is that if you have a problem in which you have a set of solutions that you can enumerate, you don't need to have any optimization. Just look at all solutions that you want to have a look at, and just select the one that is the most appropriate one. So you need to be able to do simulation, and this is just one reference, EPANet, which became very famous since it was established at the early 90s. So that's a major program, freely available and very, very, very successful. Now, so this is a map of different problems which are connected to water distribution systems. Now we have those problems. Now how are we going to solve them? Now again, what I'm referring here is to problems that we would like to optimize. We would like to do some sort of optimization. Now when we look at a problem which is optimizing something, we have an objective function in which we are trying to minimize or maximize. We might have more than one objective function if we are looking at a multi-objective problem, like for example, reliability and cost. And we have a set of constraints that we want to fulfill. So how can we do this? Here are three methods, or three category methods that I will, at the examples that I will show, I will focus on. The first one is embedding. If the problem is really simple, then you can simply write a linear programming model. A linear programming model is that the objective function is linear, all the decision variables are just at the power of 1, and you have a set of constraints which are linear equations. So LP, or linear programming, is extremely popular, extremely efficient, and if you have that model running, or if you have a problem that you can cast in a linear programming model, then that's great. Do it, and you have a very efficient way of solving it. For example, the problem of least cost design whose layout is branched is a problem that can be embedded and can be a linear programming model. Anyone of you who knows, this is going back to 1968. There is a famous paper of Carmeli et al. That invented this idea. The other thing which is very, very popular now is the so-called linking. What do we do in linking? In linking, we have two stages. One stage is simulation, which is running different scenarios. And at the upper stage, we have a heuristic methodology. People are using genetic algorithms a lot since 1994, something like that. And those two levels are talking with each other. We'll see in a moment an example. And different decision variables are plugged into simulation. And the genetic algorithm is giving guidance on how to move from that decision variable space to another point, or how to move within the decision variable space. Now, hybridizing is like linking, just the simulation model is a little bit simplified. When you do this connection between simulation and heuristics, one of the big problems is the computational time, which you cannot avoid, because genetic algorithms or heuristic optimization is you're really using all the force that you can have to solve a problem. Now, since you're solving the problem lots of times, if you have a simulation model that is just running 3 minutes, what is 3 minutes? 3 minutes is nothing. But if you think about 10,000 evaluations, so you can think a little bit about this, it's about a week or 10 days. Do you have 10 days for running one model? You can run it parallel if you want, but the computational problem is extremely important if you do this type of approach. So on the one hand, it's very powerful, but on the other hand, it's very computational intensive. And on the other hand, which is worse, is that everyone that is doing a genetic algorithm is a little bit leaving the thinking on how to solve it using an embedding approach. And hybridizing is just a way to try and simplify the simulation stage. So I think that this slide is probably the most important one in my talk, and if some of it you will observe, then I've done my job. Okay, so that's a map. I will show now 3 example applications that are trying to demonstrate parts of the thing that I've shown here. Excuse me. Anyone who is interested to see a little bit of more than that, just a moment. If we go back just to this example, I was engaged in almost everything that is connected to here. So, for example, if you pick up aggregation and number of loadings and flow and head, I was engaged, flow head and water quality and aggregation, everything. I haven't done anything on maintenance. I've done unsteady reliability, a lot of things which are connected to security. So what I'm trying to say is, I've selected 3 example applications that will demonstrate some of the things that I've shown here. But if you want, just go to my website, and there is a list of there are 87 papers, journal papers. You can go there and pick anyone and have a look, and everything is open. And if you have any questions, you can approach me, and I will be more than glad to assist you. So here are 3 example applications. Here is example 1. Now, this problem is entitled Desalinated Water Sources Inclusion in Optimizing the Operation of Water Systems. That's a problem that is very much important in Israel. And it is important in Israel because Israel has, on the one hand, a shortage of water, but on the other hand, it has a coast. And a lot of desalination is being done lately, and desalinated water is injected into the existing system, and there are different problems that are happening because of that, because of water quality issues. So this is me. I would like to acknowledge Ori Lahav. Ori Lahav is a faculty member in civil and environmental engineering, and Elad Zalomons, that is working with me for quite a while, that is a private consultant. Okay, so, and again, if you want to have, to look at more details, this is the reference that you need to read. Okay, so a little bit on introduction, objective, decision variables, constraints, methodology, example, application, and conclusions. Now, this presentation and the 2 others that will come afterwards are to some extent technical. All the technical issues I will leave aside. I will skip them. We'll look at them just in a glance, and we'll keep forward because those are technical things. Anyone who wants, again, to look at those more in depth can do this, but that's not the most important thing. So in terms of introduction, what do we need? What are we solving? So the problem here is the following. You have desalinated water on the shore. You have surface water. You have groundwater. And you're mixing them in the same water distribution system. Because of that, you might have very difficult, very severe problems which are connected to water quality, which are not connected to contamination. They are connected to water quality issues because the stabilization of the water is different. Water that is coming, desalinated water, has almost no minerals. On the one hand, groundwater and surface water has a different properties, and when you mix them, you can have the so-called red water. Excuse me. What is red water? I think that, excuse me, I think that all of you has experienced the idea, has experienced red water. If you go out of your apartment and you come back after a vacation or something, and you open your tap and you have that brown water that is coming out, that's red water. Because everything that is everything that is attached to the pipe, or some part that are attached from the pipe, are going into the water fluid and are going up going out at the tap. So problems occur when waters that have different chemical characteristics, are blended, and especially when desalinated water sources are present. So, and what has been found is that what we need to take care of, or what is characterizing the stability of water, is the so-called CCPP, or calcium carbonate precipitation potential. That's a chemical property of the water that we need to be able, or we need to control to be of a positive level. And when desalinated water are blended with groundwater, even if both sources have a positive CCPP, or that value, still you can get the phenomena of red water. Here is the water distribution system of Israel. Here is Haifa. Here is where the Technion is located. This is the only surface water in Israel, the Kinneret, which is about 4 billion cubic meters. That's the entire volume of the Kinneret. This is the national water carrier in Israel that is supplying water from the north to the south. That was a very big project at the beginning of the 1960s, a national big project, and still working. And those are desalination plants that are being built on the shore, and more are being built as we go along. And the problem is that you're injecting those type of waters into the distribution system, and all of them are being mixed here. So water is supplied here from, or traditionally it is supplied from north to south. And now, because we have desalination plants, water is injected, and to some extent water can also go the other way, which is really an evolutionary in the way that water distribution system in Israel are operated. And this is the Dead Sea, and this is the Mediterranean Sea, and the total consumption of Israel is about 2 billion cubic meters per year, which includes everything, industry, agriculture, and water in the cities. Okay, so that's a phenomenon of red water that I've just mentioned, and we would like to control this. So here we have built a model which have the following objective, decision variables, and constraints. And we solved an optimization model. Now, again, what I would like to emphasize here is even if you are not solving an optimization model, if you're just doing simulation, if you will think on what you want to do in terms of what is your objective, what do I want to accomplish, what are the decision variables? For example, I would like to accomplish reliable water supply to consumers. What are the decision variables? The decision variables are where to place new pipes and how to operate the valves. Those are the decision variables. What are the constraints? I need to have a minimum pressure at specific nodes in the system. I need to maintain a minimum water level at the tanks. So if you think along these lines, this makes things quite easier to absorb. It really makes kind of an order on the way that you are thinking on problems. But going back to this problem, the objective is to minimize both the cost of pumping and the treatment, and we are looking for a positive CCPP. Decision variables are connected to how are you going to hydraulically operate the system, and to what extent are you going to treat the water at the desalination plants, and constraints are connected to pH and CCPP. Those are constraints which need to assure water quality that will not cause red water problems. And we have also constraints which are connected to the hydraulics of the system, that is minimum pressure and levels at the tanks. So we'll see this in a moment. The methodology here is, without getting into the details, this methodology is connected to the second category that I said, the category of linking a simulation model with an optimization model. Here the simulation is a little bit more complex, but the idea is the same. We are using simulation for hydraulics and simulation for chemical species. So here is the figure. Here are the two levels. This is EPA-NET, or simulation model, and this is an optimization engine. And those two levels are talking to each other. For example, this OptiGA, or the genetic algorithm, is giving to the simulation different operating pumping units. That's a binary. Which pump is going to operate at which time, the unit treatment cost, degrees of valves opening, and things like that. And these two levels are talking to each other. So the EPA-NET is giving back the solution, and OptiGA is giving down a new set of decision variables, and this one, this software STAS-OFT4, or that package is simply doing the chemical analysis, and we would like to maintain CCPP and pH, and if we get solutions which are not feasible, solutions that are not fulfilling the constraint, then we are giving them a penalty and stuff like that. But this is extremely typical on solving complex water distribution systems, and there are a few already available software on doing this, because that's extremely robust in terms of receiving solutions. But again, the price is the computational effort. Now here is just 2 screens of a program that we have developed for doing this, genetic algorithm inputs and the way that the problem looks like. Not very important. And we have here, okay. Speak slower? Okay. So what we have here, let's see if this is working. Okay, let's continue. So what we see here, this is just the main screen. Okay. I've never felt so important, I must admit. Okay. So what we have here, this is the main screen with different water quality constraints, and this is a genetic algorithm. Okay. Here is an example application. Again, you see that's a small example. We have 3 pumping stations here, and we have here again 6 nodes. That's not a real water distribution system, but it captures the idea of incorporating everything. We have here 3 sources with 3 different water qualities. So this is like a groundwater source, this is a desalinated source, and this is a surface water source. And again, those are details, technical details, which are connected to the running, which is not very important. And here is something which is important. Here, what you see here, this is a solution or the outcome of the model. So for example, what we are able to give here is the scheduling of the pumping units. Which pumping units are out of these 3 is going to work at each of the 24 hours. This is what you see here. Just a moment. Okay, what you see here, this is the pressure distribution at this node. And what you see here, this is the way, this is important, this is the way the tank is behaving. So you see that the tank starts here, this is 12 midnight, and it goes back almost to the same level. Now this is a constraint. So we start 12 midnight or 6 in the morning, we start 12 midnight. We start 12 midnight here, and we are coming back at the end of the 24 hours to the same level, or approximately to the same level. Now, what you see here is again very important, and we'll see in a moment a message that I would like to deliver, and that is, you see that the energy tariffs or the electricity tariffs change over day. So during night, the electricity tariff is very low, and here the energy tariff increases, and here it's a little bit lower than this one, and here again it's low. Now see how the tank is behaving. It's filling during low tariff hours, and it's draining during high tariff hours. And this is coming out of the optimization. Now this is very important because this is connected to engineering judgment. We are solving problems which are using sophisticated optimization techniques and stuff like this, but at the end or at the beginning, this is an engineering problem. So if the solution doesn't make sense, then we need to ask the question, why is that happening? And here, this is the beginning, and what we saw before is the beginning and the, just a moment. Okay, what we saw here, this is the beginning level and the end level, which can be within a tolerance of 10%. This is the water quality. Here, you see this is a CCPP, one of the water quality parameters, and you can see here that you will receive minimum CCPP values. So those constraints are binding. We'll come to this in a moment because this is, again, very important. We are doing sophisticated optimization, genetic algorithms. You'll see in a moment ant colony and other things. But again, we are solving engineering problems. Now, how can we know that the solution that we are receiving is optimal? The answer is we cannot. We cannot know that the solution is really optimal from a mathematical point of view. But it is really important. The answer, in my opinion, is not. It's not really important. What is important for us for solving this is to improve existing solutions. So if you have a water distribution system that is pumping, and there is an example that is pumping in Israel, water is pumped from the shore to Jerusalem, and the elevation is really high. It's about 400 or 500 meters on a very short distance, and energy is really a high issue. So if you're able, doing optimization, and even reduce the amount of energy that you're consuming just by 4 or 5%, then you're saving lots of money. Is this really an optimal solution? Who cares? You're saving money. So that's very important in the way that you're thinking, on the way that one should think on solving these type of problems. Now, how can we say, or how can we know that a solution is good? So there are different heuristics that I've written here, the way that I'm looking at this, and which can give you a clue whether what you are doing makes sense or not, whether what you are doing is correct or not. The first one is to be very close to binding constraints. Here is another example. If you have a problem of minimizing a water distribution system for minimizing construction cost, and you have constraints on pressures at nodes, at least at one of the loading conditions, at least at one of the nodes, you should be very close to the minimum pressure. If you are not close to the minimum pressure, that's fine. You have a feasible solution, a solution that will work. But is that solution going to be minimum? Probably not, because if you have a pipe which is very large, if you will reduce the pipe a little bit, you will increase the friction losses, and you will get a reduction in pressure, and the entire system cost will reduce. So proximity to binding constraints is very important. Now, the other thing is the way that the solution is behaving. If you're looking on one hand on the objective function, on the other hand, you look on your iterations, or the so-called in genetic algorithms generations, solutions usually are progressing not in a continuous way, but in a stair-like case. So you need to see if this is the way it works for you. The other thing is converging to the same local solution at multiple runs. So you can run the model once and again and see whether you are always approaching to the same solution or to a solution which is a nearby solution. This can give you confidence that what you are doing is correct. Proximity to boundary constraints, we have already mentioned. And very, very much important, the last point here, which is engineering judgment. Just look at the solution and see if it makes sense. Well, sometimes the optimization doesn't look, we are looking everything in a series. I mean, we cannot look at everything simultaneously. We're just looking at one problem. But if you cast an optimization model and everything is solved simultaneously, the optimization model might lead you to solutions that you have not been thinking of. But on the other hand, you might have an error in the model. So engineering judgment is extremely important here when you look at the final solution. Okay, so in terms of conclusion for this example, so that's just an example of looking on water quality problems, injecting water quality that is connected to water sources with different water quality stabilities, and trying to solve a model which is incorporating everything, the hydraulics and water quality in one framework. Okay, so that was example one, and we have done different cases. What I've shown here is just the one case we've implemented to another water distribution system, and it's open to anyone who wants to use it as a model to balance between water cost and water quality. Okay, so this was example number one. Now we are moving to example number two. Example number two is connected to reliability of water distribution systems. So this is a title of this talk, but the main issue is connected to reliability, which is a very complex problem still. And it is complex. It is complex even from the beginning. How do you define reliability? What measures are you going to take into consideration? How do you, if you have a measure of reliability, how are you going to build a model that will fulfill that reliability measure that you're taking into consideration? For example, say for example that the reliability of a water distribution system is that you are guaranteeing the consumer no more than 2 hours of shortage in a year with a probability which is higher than 0.98. This is like a return period in hydrology, if any one of you is familiar with. So, okay, so that's say that this is a measure of reliability that everyone is happy with. How are you going to implement that? That's a problem. Okay, here, this is the reference for this paper published in Water Resources Research. And again, if you want to look at all the technical details, they are sitting here. Okay, so here a little bit of background, literature review, methodology, example application, and conclusions for this example. So as I said, reliability is a probabilistic measure of system performance. And people will say the system is highly reliable. But if you talk to them a little bit more and tell, okay, what do you mean by reliability? It's always a problem. And the challenge, as written here, is to transform that general definition or measures of reliability into computational tools that will be able to solve problems and maintain a reliability measure. In terms of literature, there are two types of models that have been evolving connected to reliability. One is reliability evaluation models. Remember, when we started, I said that you cannot do any optimization if you're not able to simulate the system. So reliability evaluation models are models that are trying to simulate the system in terms of reliability. Generally speaking, if you want to know if the system is reliable or not, you need to run a lot of randomization or Monte Carlo simulations and see how the system is working. In practice, what you do, most likely, what people are doing, they're looking at different scenarios, which are looking at the most critical one and see whether the residual capacity or what is remaining from the system after something is failing is still able to cope with the consumer demand. So those are reliability evaluation models. And the other thing is, once you have reliability evaluation models, how are you going to incorporate them into design, into list or optimization models, least cost design of water distribution systems? So in terms of reliability assessment or evaluation models, those are references, again, if you want to have a look or look at those more closely. Analytical methods, which are connected more to the probability of the two nodes are being connected. In water distribution system, the fact that two nodes are connected is only a necessary condition. That's not a sufficient condition, because even though you have a connection, you might not have the tools to supply water. You don't have the hydraulic tools to supply water. The head at the reservoir is not at the right level. The pumping unit that need to pump that water doesn't have the enough capacity. So it's only a necessary condition. In electrical engineering or in computer science, it might be a necessary and a sufficient condition, but in water it's not. So those are analytical topological connectivity methods. The other is stochastic simulation, as I said, or Monte Carlo simulations. Those are the two categories. Now, in terms of reliability inclusion in optimal design operation, the first one to do anything is Su et al., which developed the so-called cut-set method, which is just looking at different scenarios of failure and trying to look at their probabilities and incorporate them in models. There are other models that are being listed here. There are, for example, a multi-objective. This is Reka et al. 2008, multi-objective for trading off reliability and cost. Salgriada et al. 2010, which is connected to reliability of distributions network using a dissipated power concept, and others. The literature is full with reliability models. Okay, now, what is done in practice in terms of reliability? As you know, still, reliability is guaranteed by taking pipes which are larger than a minimum diameter, allowing storage in tanks not to go below a specific level, having extra capacity of storage, having extra connections, but there is no explicit inclusion of reliability using these heuristic methodologies. So what has been done in this model is to incorporate the so-called topological redundancy with residual capacity. And the idea was very simple. The idea was the following. If you're looking on any system, if you're looking on a water distribution system and you're imposing on that water distribution system a load, what is the load? The load are the demands. So you can look at the demands now, at present, you can look at the demands in the future. You're imposing those loads and you're designing the system, and you're receiving the set of diameters, the set of pumps, everything, the maximum power of pumps, the volume of storage, everything. But if you're increasing that loading, you will receive the same layout of the system, but pipes will increase and the pump's capacity will increase. Everything will increase. So if something is failing, you will have the residual capacity that you are looking for. Now the problem is, what loading conditions are you going to select? So the idea here is to do two levels. One is to impose on the system virtual loadings, not the existing one. And the other stage is to solve the system for minimum cost. And so these two levels are playing with each other, and this is the so-called decomposition, because we are decomposing the system or the problem into two problems, reliability and least cost design. I'm moving on this one forward. Most of the things I've already said, but it's written here. So we are looking at those virtual increased loadings that will give us, on the one hand, a system with minimum cost, and on the other hand, will also give us a system with an adequate residual capacity. Okay, here's a little bit of technical stuff. This is a decomposition problem which we are solving. The first one who started doing this is Alperovich and Shamir. You remember the figure that I've shown before, the two-loop network. They had the same idea on least cost design of water distribution system, and here this same idea is being incorporated for reliability. This is technical stuff. This is again technical stuff, which is not very important. And again, if you want to have a look, you're more than welcome. So we have a problem that we are solving here, which is a problem of minimizing cost, and we have an outer problem, which is the loading condition problem. And this is the mathematics that is sitting behind that, which is again not very important. Okay, so how did we solve it? We solve it using ant colony optimization. Ant colony optimization is going the same lines as genetic algorithms. Genetic algorithms are trying to evolve or trying to imitate the way that nature is behaving, the way that the evolution principle is behaving. And as you know, that evolutionary said that the strongest species remains. So that genetic algorithm is trying to follow those lines. Ant colony is trying to follow the idea of ants that are moving from one node to the other. Ants are completely blind, but then when they are moving from one node to the other, they are following tracks of smell. So there was a guy in Italy whose name is Dorigo, who has done that in 1992. So that's a different optimization model. There is a reliability evaluation model here. I will skip that. Again, that's a surface subjective function, which is extremely non-smooth. Here we solve two problems with ant colony. So this is just a schematic description of how those ant colony are working. We'll go to an example application. So here is an example application which shows the essence of this idea. Again, a very simple example application, but quite general. So again, we have three sources here. You have a pumping station here, and the idea here is that we want to design the system not just for least cost, but also for residual capacity by increasing the loadings. So this is a data elevation, base demands, minimum pressures, constraints, not very important. Energy is changing over the day, so that's a real full problem that is connected not just to the design of one loading condition, but to a design that is changing over time. And again, these are costs which are connected to the pipe diameters. This is the program that we have constructed for solving the inner problem and the outer problem. And this is how they are connected. And we'll move forward to the results. So here, what you see, this is the main message that I would like to show here. What you see here in black, those are the diameters that are going to be selected, and those are the pump's maximum power. Those are the diameters. This is the maximum power of, this is the maximum volume of the tank. This is the maximum power of this pumping station, and this is the maximum power of this pumping station. Everything that you see here in black. What you see here in red are the expansion of the system. So the system, it's like if you're blowing something, and it's really becoming fat. So how fat are you going to blow that system? It depends on the loading. But since you don't know the loadings, there is an iterative scheme. So what you see here in red, those are the blowed system, or the system with higher dimensions. Not everywhere. For example, you can see here that this is a diameter that was 254 millimeters and came out as 152. But generally speaking, you can see that everything is increased. This is the volume with reliability considerations, and this is the new maximum power with reliability capacity. And those are simply the virtual loading. So, for example, here, the virtual loading here should be 1.16 higher than the normal loadings. And this is a little bit the way that the objective function is progressing. You can see here a little bit what I've said before, the stair-like progression. It's not very dramatic here, but you can see that it's falling down with stairs. It's not falling down continuously. Those are a sensitivity analysis that we made on the failure duration, on the algorithm, and etc. Not very important. Here is a picture which is important. This is the surface function as you've seen before, but with two flows here at QD and QC. And you see here that this is, again, not very smooth. OK, we'll move forward. Conclusions are simply that we are using a new or what is proposed here is a new direction of trying to incorporate reliability by changing the loadings on the system and seeking the optimal loadings that need to be imposed on the system to get not just a system with minimum cost, but also with adequate reliability. Okay, last example. Last example is this one. This is more complex than the others. This is called, this is about incorporating uncertainty into water distribution systems design. So when we looked at the map, I said that everything that we are doing is deterministic. But in nature, everything is stochastic. So how are you going to incorporate stochastic features into water distribution systems design? So here is an idea of doing this in a different way that has been done so far. So far, most of the models are using the so-called Monte Carlo simulations with a lot of computational effort. Here, we're using something else, which is coming from an idea which is called chance-constrained or chance-constrained linear programming. We'll see this in a moment. And again, this is a paper that was published in Hydroinformatics that gives all the details of that example. There is one which is more advanced than that one that was published in Water Resources Research. We'll see this in a moment, so you can have a look at all the technical details. So here, a little bit on introduction, methodology. We are using the so-called robust counterpart for including uncertainty into water distribution system, and example applications and conclusions. So, so here, what we tried to do is to include into water distribution system uncertainty in the least cost design problem. And we try to do this differently than all the modeling efforts that are being, have done that before. So the so-called robust counterpart, I will move forward a little bit because it has a lot of technical details here on how to do this. We are formulating the so-called robust counterpart. Then we are formulating the uncertainty set, and then we are solving the generated problem. Again, I'm moving forward because that's more technical. Here is something which is important. If you are looking at these two axes, say for example that this is deviation from mean parameter 2. Say for example that this is demand on the system. So here is demand number 1. This is demand number 2. This is a nominal value, the average value. The average value. So if you're designing for the average value, this is one way. The other way is you might look at the worst case scenario. What is the worst case scenario? That everything is at its extreme. So it's not the average, it's the highest loading in the system. That's okay. But if you will do this, then you might receive a too conservative solution, which will be expensive. So you might do this, but you can also have a robust policy, so you can reside everywhere here in this circle or in this ellipsoid. So here, again, this is the average solution. This is the worst case scenario, but you can reside here at any point. So for example, you can choose a demand that is a little bit higher of this axis and a little bit higher on this axis, and residing here or wherever you want. Okay, so robust policy neglects simulations worst case, so we're not looking here, but at this point, what you'll see in a moment that if we want to have this point, we can incorporate that as well. Okay, and this is just a three-dimensional figure of what I've shown before. Again, this is mathematics on the robust counterpart. With this bottom line, again, it's not very much important at this stage. At water distribution system, we have these two basic laws. One is for mass continuity and one for energy continuity. Again, that's mathematics which is connected to the way that we are incorporating the robust counterpart, and we'll come in a moment to the bottom line. So this is what we are incorporating in the model, and it comes out that out of all this, say, complex mathematics, all that we need to do is to add a component to the demands using theta, which is a user-defined value, which we'll see in a moment, and the coefficient and the matrix, which is called delta I, which is incorporating an uncertainty set. And again, I won't get into the details of this because that's too much. So how to compute delta I? So this is a little bit on how to compute delta I. Again, I'm moving forward. This can be found either in the paper or better at the book of Bental et al. So I'm moving forward, and I'm coming to example application, because this will demonstrate you how or what this methodology can do for you, which is very nice. You'll see in a moment. So here, for example, you have a constant head source. Say that this is a reservoir, and you have here 4 consumers. You have here 4 consumers or 4 demands: D1, D2, D3, and D4. So this is, for example, 3.5 cubic feet per second, and this is 2 cubic feet per second, and say that we are assuming that these demands are uncertain. So they are not deterministic. They might be between a minimum and a maximum value. Those are data of the example. Again, not very important. There is a minimum pressure constraint here of 30 meters at all nodes. And here is the main point. Here on this axis, you can see this is D4. This is the demand at one of the nodes at CFS, cubic feet per second. And this is the demand at node 3 in cubic feet per second. Now, if you're taking the nominal value, that's the nominal value, the average value, which is 3.5 and 2.5. Now, in reality, you can get any number in a box. It can go to a minimum and to a max. Any number here in this box might be realized when the system starts to work. So, for example, you say, OK, I'm going to design a system. I have a master plan for a system, and I'm anticipating that that neighborhood is going to be very large in 10 years. And we're anticipating that the demand is going to increase by 20%. And we are designing for this. But the demands are not increasing by 20%. It is increasing by 50% because of different reasons. I don't know, quality of life, more people are coming in, whatever. So if we are designing here using the traditional methodology, what we are receiving the following. Just a moment. We'll look at this one. OK. What I've said before is that we can design the system using different ellipsoids. We'll come to this in a moment. But again, if you are looking here, just a moment. OK. Again, if you are looking here at the average values of D3 and average value of D4, and this is the nominal point, any point here can be realized in the real water distribution system. So you can have those demands sitting here or here. So you can have scenarios which are different than the ones that you have designed for. So what does this picture say? This picture says that if you are designing the system with those levels, then all these demands if those are being realized, the system will not be feasible. You will not be able to supply the consumers the adequate pressures that they were promised to be supplied. Those will be feasible, but those will not be feasible. Now, if you're using a value that was at that methodology, which is called theta, which is giving you the uncertainty set on how big you want the uncertainty set to be, if you're taking this theta value, you're incorporating all these demands. The cost is increasing to 241K or 241. Remember that the cost before that was 184. So you're moving from 184 to 241, but all the demands are feasible now. So you can select any demand here in the system, and the system will still be feasible. Now, the beauty of this methodology is that you don't need to do stochastic simulations. This is only a one deterministic model that you are solving. And once you have solved that, you are doing stochastic simulations to check whether your model is working or not. But you're not doing this computational intensive work of doing so many Monte Carlo simulations and selecting decision variables. So this is very nice. And we'll come in a moment to see what are the limitations of this. So you can choose different uncertainty sets which are connected to the value of theta. For example, if you are choosing theta 0.9, you get this figure. We'll move forward. This is another graph which is very important. What you see here, you see the blue one is the cost. So if you want to have a very robust, if you want to have a very conservative design, taking into consideration the worst case scenarios, you're going to pay this amount, 240. If you want to be just at nominal values, you will be at the lowest value. And what you see is, and this is a trade-off between the value theta, that is a measure of the uncertainty, and the cost of the system. And what you see here in green, this is the reliability of the system. Here, the reliability of the system has a different meaning. This means the amount of solutions that are feasible. So for example, if you are taking the lowest cost solution, the nominal solutions, only 60% of the demands will be feasible out of that box. You can choose 40% of those demands, and if those are implemented on the system will not be feasible. You will not be able to supply the consumers minimum pressures. Now, if you're increasing theta, you can see that the green line is also increasing. And if you come to here, you have the highest cost of the system, but with the highest reliability. So any demand that is going to be imposed in the system will be feasible, but it will be the highest in terms of cost. So that's the main message of this methodology. So this is a deterministic design. This is the worst case design. And we've done here different things which are connected to the correlations of the demands. I will skip that. This is another trade-off between reliability and cost. We've done this also on the Hanoi system, showing the trade-offs. I will move forward. And again, cost and reliability. Okay, conclusions and future work which is connected here. The robust counterpart, the idea here is very nice if the constraints are linear. If they are not linear, it becomes a problem. So here we have done something which is continuing this idea, and that is to try to linearize the friction head loss equation. And as I said, there is a paper that was published in Water Resources Research, and if you go to that website, you will find it as well, or you can approach me and I will send it to you. So, and again, here it's like future research, but this has already been accomplished. Okay, now we are coming to the last slide, which is challenges. Now, in terms of challenges, if we are coming back to that figure that we started from, everything is here on this slide. Now, people have done a lot on sizing systems, on doing least cost design system. This is extremely saturated. Whether you are doing branch system or loop system, gravitational and pumping, trading off cost and trading off different layouts of system and cost, this is extremely saturated. Also, operation models are also quite saturated. Looking at systems for scenarios and looking at scheduling pumping units, that's also relatively quite saturated. Now, what is not saturated, or what can be done, which is quite a new field or has not been absorbed yet in water distribution system, is incorporating uncertainty or stochastic features. Like, for example, you've seen the robust counterpart as a way of doing this, taking uncertainty and incorporate it into models of water distribution system, but doing this a little bit different than what has been done before, like doing lots of stochastic simulation, etc. The other thing which I can say here is that If you go back to the 1960s, for example, when water distribution system design operation started to evolve, people started from embedding, from thinking on how to do and how to embed, how to do tricks to incorporate constraints. And they were thinking a lot. In 1994, the first genetic algorithm model came out. That was a paper of Angus Simpson et al. And everyone that did water distribution system were amazed, because suddenly the problem was not of an importance, because you had a tool that was able to solve everything. I mean, you can do these two links between simulation and genetic algorithms, and everything can be solved. So instead of concentrating on tailoring a methodology, there is a genetic algorithm, there is a vehicle, you can go on that vehicle and get a solution. To some extent, it's very good, because you can solve real problems, etc. On the other thing, it's really reducing the pressure on anyone to think on the real properties of the system, and that's not a good thing, because you can do maintenance, you can do leakages, you can do everything using that two levels. So this was in 1994, and I think that nowadays, if you want to publish a paper which is connected to these two levels, this will be much more difficult than it was 10 years ago, because it's saturated. So what's the point? You're doing, again, simulation and genetic algorithm. That's not innovative. That's not something that people really can learn from. So that's very important. So incorporating stochastic or uncertainty in models is one way. The other thing which is completely not explored, is taking into consideration water quality issues and unsteady flow. So if you have unsteady flow can go back into the system. There can be a reverse flow. How do you size surge devices in the water distribution system in an optimal way? Now, obviously, it's not just one objective. It's not just the cost of the surge control devices. It's also the trade-off between the damages to those that might happen because of a transient and the cost, etc. Water quality falls, for example, excuse me. Water quality issues that are connected to transients are also an issue. So the message here is, if you want to do something which is connected to water distribution system, and you say, okay, I want tomorrow at 5 o'clock in the morning, I want to start doing something. So if you want to do something, then I think that taking any of this map, any combination, water quality, unsteady, or any other problem, and incorporating uncertainty say in a nice way, in an intelligent way, are really challenges. So that's the main thing, and that's okay? Okay, thank you, and I will be glad to answer any questions you might have. Thank you.